Hello, I'm Jason. Welcome to this lesson of the Laplace Transform Tutor. In the last section, we did a lot of talking about the reasons why Laplace Transform might be useful, a lot of the overarching ideas there, and then we derived the essential Laplace Transform for some very important function class, which is the exponentials, right? Because those things, if you remember differential equations, those things pop up all the time. Here we're going to derive another Laplace Transform, essential one here. And again, I could just give this to you. Most books will just give this to you or give you a really short derivation without showing everything. I think that sometimes in math doing a real derivation can help you, and sometimes it's not worth it. So later on we're going to get some stuff where I don't think it's worth it, but here I think this is worth it. So let's learn how to take the Laplace transform of a very important function, t to the power of n. And notice we're talking about functions of time. And so in this case, n is greater than 0. So in other words, this is going to let you understand and learn how to take Laplace transforms of t squared, or t to the fifth, t to the 1, whatever. Anyway, when you have powers of t. So what we want to do is really just apply the definition of what Laplace transform really is. So what we're going to have here is we'll say that this is going to equal, this Laplace transform of this guy is going to equal the integral from 0 to infinity e to the minus s times t. Then we have to put in our function. In this case, it's t to the power of n, which we don't know what n is. It could be, t to the fifth, t to the sixth, whatever. And we're integrating, of course, over time. So if you know how to look at this and write the answer down, which most people aren't going to, I don't know how to just look at it and write the answer down, then that's the Laplace transform, and you're golden. For most of us, we have to work through that, and again, it's given to you in a table of Laplace transforms, but I want to go through how to integrate this to kind of show you where it really comes from. Now, the best way to do this is integration by parts. And if you haven't studied integration by parts in a while, it's kind of one of those things you have to kind of keep in your head, because as you march through more advanced math, it's going to pop up over and over again. Some of these things you just have to remember from calculus. So we're going to integrate by parts. So we'll write that down. Integrate by parts. And if it's been a while since you've done this, it's okay. I'll walk you through it. So basically, we need to define a u and a dv. So we're going to say u is equal to t to the power of n. dv is equal to everything else in this integral. So we have the exponential e to the minus st, and we have to carry that in. So what you do is you take one part of the integral, define it as u, take everything else, including the differential, and define it as dv, and then we're going to make a substitution. But before we can make a substitution, we have to take the derivative here. So we say that du is equal to, how do we take this derivative? It's n times t to the n minus 1 dt. When you think about this, don't get too worried about all the n's everywhere. If it's t squared, or let's say if it's t cubed, what's the derivative with respect to t? It's 3 times t squared, which is n minus 1. So you take the exponent, put it in front, and then you have n minus 1 up there. So that's the derivative there. And then to march in the direction here, we need to solve for v. So we're going to integrate e to the minus st dt in order to recapture what v is here. And so v, the way you integrate this is an exponential. You kind of need to at least get a little bit comfortable with integrating exponentials. The way you would do it is by what we did in the last section. You could do u is equal, some substitution is equal to this whole exponent. But what you're going to find when you integrate exponentials enough is that what happens is it's the derivative of the exponent, in this case it's negative 1 over s, is basically going to come out. And then the exponential, of course, is indestructible. So that stays there, e to the minus st. So again, you can integrate this by substitution and doing all the same stuff that we just did in the last section to do this. But what you'll find is that when you're integrating, let me put it this way. If it were just e to the t and you integrated it, what's the answer? It's e to the t. So when you integrate e to the minus st, the core part of the function remains indestructible. What you have to do is bring out in front of it the 1 over the derivative of the exponent. The derivative of this exponent with respect to time would be negative s. So it becomes 1 over negative s in front. That's not a magic wand. That's what happens whenever you take and substitute u and do the substitution, integrate it, plug it back in, and all that stuff. This is what pops out as the answer. So now we have four important pieces of information, u, du, dv, and v, and we can actually apply this thing that we call integration by parts. And the way that works is it's u times v minus the integral of v times du. And we just have to plug it in and crunch through it. It's going to be a little bit ugly, but we're just going to have to do it. So u is equal to this, so we're going to have t to the power of n. V is equal to this, so I'll open a parentheses, negative 1 over s e to the minus st, right? So it's u times v, but don't forget that you're still evaluating it from 0 to infinity. That's this part here. And then you subtract the integral, again going from 0 to infinity, of v, which we have here. So I'm going to write this as negative 1 over s e to the minus st, right? That's what v is. Du, which is this part here, which will be n times t to the n minus 1 dt. Now, I don't know about you, but this gives me kind of nightmares at night. I mean, it looks ugly. It really does look ugly. But you kind of have to just trust that when you see something ugly, you double check, take a step for a second, take a minute, make sure that you haven't done anything bonehead in writing that down. Okay? And then once you're convinced that you didn't, then you just have to plow through it. Now, I will tell you that these limits of integration being 0 and infinity and all these exponentials running around everywhere is going to simplify the answer dramatically. Because anytime you have e to the 0, you end up getting 1, and e to the negative infinity is always going to give you 0. So in the end, it's going to get much simpler, but you do have to keep track of all of these signs every single step of the way. And so that's what we're going to do right here. So before we plug anything right here, let's just do a little quick, that's not really a simplification, but let's change colors and kind of tidy things up. Let me put it that way. So this negative, I'll put negative t to the power of n 1 over s e to the minus st from 0 to infinity. That's this part here. And then what I have over here is I have this negative 1 over s. So what I'm going to have here, this is going to be a positive, right? When you think about it, I'm integrating over time. So this n acts as a constant, right? This exponential you can't pull outside because it's got a time there, but this 1 over s and this n can both come out, and this negative sign can both come out, so that's going to make it a positive, and what actually comes out is n over s, integral from 0 to infinity, e to the minus st, and then you have t to the n minus 1 dt, all right, dt. So we still have to evaluate all of this stuff, we know that. And we still have to evaluate this stuff, we know that. But when you do integration by parts, what you're really looking for is, the way your integration by parts works is you do the substitutions, you apply the thing, and hopefully this integral that you get over here on the right-hand side leads you to some sort of simplification, or it's maybe a simpler integral. So when we study this, okay, I want you to cover everything up, cover up the n over s, everything. Just look at this. So what you have is e to the minus st dt, and you have something here. Doesn't this look like another Laplace transform? Remember, it's e to the minus st, and then you have whatever function you're trying to transform here, and then it's integrated over this. So if I had to write one thing that I wanted to point out to you, is that this limit of integration is really the Laplace transform of t to the n minus 1. So what happens is we're trying to transform, go way up here, trying to transform t to the nth. And what we get is a bunch of junk multiplied by the transform of t to the n minus 1. So as I apply the Laplace transform, I end up with another Laplace transform with 1 less in the exponent. That's going to be important in a minute. All right? So before I move on to the other board, let me at least simplify this part, because this can be done right now. So what we want to do is evaluate this whole expression at these limits of integration. So what I'm going to have then is I'm going to plug in here infinity into here. So I'm going to have negative infinity to the power of n times 1 over s e to the negative infinity minus, so that's plugging in infinity into this block, minus the lower limit of integration, which is going to be, here I'm plugging in time, so it's really going to be negative 0, or it doesn't really matter if it's negative 0 to the nth power, and then I'm going to have 1 over s e to the 0. what I'm essentially going to have here, when you really think about it, is this becomes, everything is driven by this term, e to the negative infinity. Yes, there's an infinity here, I see that. But the negative infinity is basically, it basically acts as an e to the infinity on the bottom. And that's going to go to infinity faster. So I have basically infinity term in the denominator that's going to drive the whole thing to 0 as the limit is actually taken. You do have an infinity here, I agree, but this exponential to the infinity on the denominator is going to drive it to 0. And then here you have e to the 0 gives you 1, but this guy is just multiplied by 0. 0 raised to the any power is just going to give you 0. So this term is going to basically go to 0 as well. So all of that math basically just eliminated this whole front end here, and the Laplace transform is basically simplified as follows. What we have found is the Laplace transform of t to the power of n is equal to what we have on the bottom, which is n over s, right? N over s times the Laplace transform of t to the n minus 1. Make sure you look at this. Make sure you reconcile it with this. We've applied everything. We found that it's equal to some constants with an s down here, and then you have the Laplace transform of a related exponential, but one less. All right? So you might circle this in a table and say, well, okay, that's kind of useful. But what happens if I put t to the fourth in here and I want to take the Laplace transform? Then I have to find Laplace transform of t to the third. All right? But you can see it's recursive, because once I know I'm taking Laplace transform of t to the third, I can find Laplace transform of t to the second is required. And then I can say, well, I need to know what that is, and then I have to find t to the first, and then I find t to the 0, and so on. So it's a recursive thing. So if you keep going recursively, then what you get is a really, really cool, I think, result. And the cool result is the following. The Laplace transform of t to the n is equal to n over s times the Laplace transform of t to the n minus 1. But let's say I want to apply the Laplace transform of t to the n minus 1. So what I'm going to have is this stays out in front. It'll be n over s. But then when I apply this one, notice what I did. When I applied the Laplace transform here, the n, whatever the exponent was, came out here, and then I put an s on the bottom. So if I do it again, whatever the exponent is going to come out n minus 1, and then I'm going to have another s on the bottom. It's going to make it s squared, right? And then I have a Laplace transform of t to the n minus 2. So what I'm trying to say is the Laplace transform of t to the n became this. But then if I try to evaluate this, it'll be n over s times the Laplace transform of this. The exponent comes out, another s goes to the bottom, and you get this with yet another recursive, down the rabbit hole kind of situation. And so if you keep doing this over and over and over again, what you end up with, the numerator ends up becoming n factorial, because n times n minus 1 times n minus 2 times n minus 2. If I keep going, it's going to be n factorial over s to the n. And then eventually, if I keep going and going down this rabbit hole, I'm going to get to a situation where I'm going to take the Laplace transform of 1. Because eventually, let's say I start out with t cubed, or t to the fourth. Then let's say I start with t to the fourth. Then I'll have to find the Laplace transform of t to the third, and then t to the second, and then t to the first, and then t to the 0, but anything to the 0 is 1. So eventually, if you keep going far enough, you're going to have to find the Laplace transform. In the limit, if you take the whole thing, you're going to end up having to find the Laplace transform of the number 1. And we just learned in the last section that the Laplace transform of 1 is, so let's write this down, s to the n. Laplace transform of the number 1 is 1 over s. We just figured that out in the last section. So what you end up getting is n factorial, and then you have s to the n times s, so you have s to the n plus 1. So the Laplace transform of t to the nth power is n factorial over s to the n plus 1, and we of course want to just for completeness, we'll say s is greater than 0 to keep the denominator away from any kind of singularity. This is what you need to remember. This is what will be given to you in a table of Laplace transforms. In truth, seriously, I could have just opened this section and just given you this and said, hey, Laplace transform of what are going to end up helping us take Laplace transform of polynomials, t squared, t fifth, t to the seventh, whatever, is given by this, and just use it. I could just do that. Of course I could, but sometimes I think derivations are useful if they only just show you how to deal with the integral, which is going to be important, and also they show you that these things don't come out of a black hat. They don't come out of a magic rainbow. They're just calculus that comes about from applying the definition. All right? So what it's telling you is, if I want to take the Laplace transform of, let's say, t squared, then since the n would be 2, I would take 2 factorial on the top, and then it would be s to the 2 plus 1. So it would be s cubed on the bottom. Right? Whatever n is goes here, and whatever n is goes here. So taking it from the top, real quick, what happens is we apply the definition, t to the n. We have to integrate by parts. We set this part of the integral equal to u. We set everything else in the integral equal to dv. We do the stuff that we need to do for integration by parts, and then we apply uv minus integral v du. That's what integration by parts is. U comes here, v comes here, apply the limits of integration, minus the integral of v, which comes here, and then du comes here. All right? So we're just applying it there. We just tidy this up, and then inside here we realize that n over s are constants. They come out. We get a positive sign here. E to the minus st times t to the n minus 1 stay behind on the inside. And then we recognize that this integral is just the Laplace transform of t to the n minus 1, because this is where the function of time is in that integral. When we apply the limits of integration, we put infinity in here, and then we put 0 in here. We realize that everything drops away to 0 over here, and all we are left with is n over s times the Laplace transform of this. So our conclusion is that the Laplace transform of t to the n is n over s times the Laplace transform of the same thing with one less in the exponent. All right? And so then we go down that road. We say we write this down, and we say, okay, well, if we want to do n minus 1, I would pull another n minus 1 out and another s on the bottom, and then it would be n minus 2. And I could keep going and going and going. Eventually, I'm going to get t to the 0, and if I take that to the limit, it's going to be n factorial on the top and s to the power of n on the bottom, and then I still have the Laplace of e to the 0, or t to the 0, which is 1. If I kept going, if I started with t to the 5, it would be 5, 4, 3, 2, 1, 0, and then you stop because you know, you don't go recursively anymore. You know that this is just equal to 1 over s at that point. You can stop the recursion, and so the answer is n factorial over s to the n plus 1. I think it's a really cool derivation. Occasionally on an exam you might be asked to derive something like that, and you need to be comfortable with the definition of the Laplace transform. You have to be comfortable with taking integrals. You have to be comfortable with improper integrals. You have to be comfortable with techniques of integration, especially integration by parts. So, like I said, understanding the basic concept of what a Laplace transform is pretty easy. Deriving these things, you have to know some calculus, all right? But I will tell you, though, that even though I'm harping on, hey, you have to know some calculus, really the conclusion is this is what I want you to know, right? And we're building our table of Laplace transforms. I got a couple more that I want to derive for you, just to kind of get your feet wet. And then what we're going to do is we're going to summarize these important ones on a table, and then after that point, you don't have to really do quite so much calculus. You can use these basic ones to kind of tackle more complicated problems. That's where we're going. So follow me on to the next lesson where we will take the Laplace transform of some more complicated functions, and you'll see exactly what I'm talking about.